L'Hopital's rule is one of those rules that is useful for certain applications and is pretty easy to use. It's perhaps a little bit mysterious why it works, but for the moment we'll just talk about that it works and revisit the why it works once we have Taylor series under our belt, because Taylor series make a very nice explanation of how L'Hopital's rule works. But the basic idea is I'm interested in finding the limit of a ratio of two functions. So let's say those two functions are f and g, and they have continuous derivatives on some little region around, but not necessarily including the origin. So the picture, here's the x-axis, and here is the y-axis. My functions need to have continuous derivatives, at least on a set that looks like this. So this region here, this region here. If they happen to take on values at the origin, that's perfectly fine. It's just not required. Okay, and so what it says that if either the two functions go to 0, so you have like a divide by 0 situation because f goes to 0 and g goes to 0, so you have a 0 over 0, or if both limits are infinite, so you have infinity over infinity, then what L'Hopital's rule said is, well, if that's the case, you can replace the limit that you'd like to compute here with a different limit, the limit of the ratio of their first derivatives. Now, one thing that often happens in calculus problems is that you'll do L'Hopital's rule once, and then you'll have to do it again, and maybe again a few times, taking more and more derivatives until finally you find that this situation, either f and g both are 0 or both are infinite, is no longer true. And it really is the case that you need both of them to be 0 or infinite. What happens if it doesn't? Well, if I have 0 over something that's not 0, so f is 0 but g isn't, well, clearly that limit's 0. If g goes to 0 but f doesn't, then you've got some kind of infinity. If you have 0 over infinity or something over infinity, clearly it's 0, and infinity over something finite is clearly infinity. And of course you could have some limits don't exist situations as well. So L'Hopital's rule props up in a bunch of places. One of the quickest, most standard applications is something called the sinc function. So let's take a look at what that is. So this is the sinc function, S-I-N-C. This shows up a lot in digital signal processing. And in particular, the fact that you are hearing my voice through this video at all is compliments of the sinc function. My analog audio is going into the microphone of my computer. My computer is turning it into digital data. That requires the sinc function. That conversion requires the sinc function. And that gets sent over the internet, gets housed on a server, and then when you want to play this video, your computer takes that digital data and turns it back into audio. That too requires the sinc function. Okay, now what is the sinc function? Well, the sinc function is the function which is sine of x over x. And so let's evaluate what the value of the sinc function is as x goes to 0. You'll notice sine of 0 is of course 0, and x going to 0 is of course 0. Now what is the sinc function? What does it do when you could say, well, I don't know, sine is kind of between -1 and 1, and otherwise I got a 1 over 0, so maybe this thing blows up. Let's try to get a graphic of what it might look like. So the sinc function certainly has got something like a 1 over x going on. So some kind of 1 over x kind of behavior. And so you can see that there might be a possibility of blowing up at the origin. And there's the sine function. The sine function looks a bit like this. Of course, that's the sine function, kind of badly drawn, but here you go. And just to make things a little bit less ambiguous, let me move this 1 over x over there. Okay. So really the question is, what happens at the origin? Well, since we are in the realm of computers, I think that it's enlightening to hear what the sinc function sounds like. This is what it sounds like. Okay, interesting. Kind of sounds like you might want to make some kind of use the sinc function for a beat. Perhaps you might make it play a bass line. I guess that's enough of that. That kind of sounds a little bit annoying, I suppose. But maybe with some extra riffs or whatnot, it might sound pretty cool. In any case, one thing that you'll probably hear is that your speakers did not self-destruct. There was definitely a definite pulse, a whoop, but that definite pulse is what happens at zero. Didn't blow up your speakers, didn't go to infinity. So that's an indication that L'Hopital's rule, when we apply it here, is probably not going to do anything too bad. So, first of all, can we apply L'Hopital's rule? Well, sine of x is continuous everywhere, so that's fine. It's got a continuous derivative too. What about 1 over x? Well, 1 over x does have a problem at the origin, but the origin's where we're interested in. And in particular, L'Hopital's rule only requires you to be approaching the origin. So 1 over x is continuous with continuous derivative away from x equals 0. So, yes, it applies. Well, all right, so putting the pieces together, we can use L'Hopital's rule to evaluate this particular limit. And it says take the derivative of the numerator and the derivative of the denominator separately. Well, derivative of the denominator, no problem. Derivative of x is 1. Derivative of sine of x is cosine of x. And look at this. This is no longer a problem because my denominator is 1. My numerator is a perfectly continuous function, so its limit exists. And in particular, its limit is 1. So, yes, no infinite limit. Now, one of the things that can happen when you're evaluating various kinds of limits with L'Hopital's rule is that it might be a little bit mysterious as to which function you want to select. And to give you an example of what I mean, let's consider this limit. This limit doesn't look like L'Hopital's rule applies at all because I don't see a ratio in sight. But actually there is a ratio. And this is what I mean by it might be a little bit mysterious. You maybe need to rewrite things a little bit to see that you can use L'Hopital's rule. And that's often the trick. That x can be written as a 1 over x in the denominator. Now it's a L'Hopital's rule situation. And notice as x goes to 0, in fact this should be an x goes to 0 from above, the natural log goes to infinity, and 1 over x goes to infinity. This is the opposite situation, the other possibility in the hypothesis. So the sine x over x business was the first condition, the limits of f and g are 0. This is the other condition, both of those limits are infinite. Okay, so L'Hopital's rule applies. Why? Because the natural log is continuous up to 0, and it's really, that's the only place we care about the limit, and so is 1 over x. All right, so moving along. Let's take the derivative of the numerator and the denominator. Derivative of the numerator, derivative is 1 over x, because the derivative of natural log is 1 over x. The derivative of the denominator is minus 1 over x squared. Okay, this is a ratio of two polynomials, so we should be able to sort this out. And in fact, notice that 1 over x squared in the denominator is really an x squared in the numerator. So after a little bit of rearranging, we'll find out that this is just x. And of course, no problems here. This is 0. So what this means is if you try to plot the natural x times the natural log of x, as x goes to 0, it becomes 0. And actually, this is the sort of thing that is nice to plot. Here is 1. The natural log is 0 there. When x is between 0 and 1, let's see, we just found that the limit is here as you go to 0. When x is between 0 and 1, x is positive. Clearly, the natural log is negative. So it looks a bit like this. Goes through 0 again. And then when x is greater than 1, both x and natural log of x are positive. So it does something like this. So this is what x ln x looks like. So L'Hopital's rule is a pretty convenient tool for that sort of thing. I would say it tends to creep up on students when they're least expecting it. And so be on the lookout. Even if you see some limit you can't evaluate just by looking at it or using some of your other tricks, if it's a product, think about whether you can rewrite it as a fraction. And of course, if it's a fraction, be on the lookout for L'Hopital's rule. But if it's not a fraction, but it's a product, maybe it can be written like that. Another little trick, which I won't show you here, but certainly shows up in plenty of examples you might try, is to move around some natural logs to turn addition into products or division into subtraction. Again, these are places in which you might be able to turn a limit that doesn't appear to have L'Hopital's rule actually turn out to have L'Hopital's rule in it.